This is stochastic processes module 8 renewal processes. In the model 1 we have presented the probability review and introduction to stochastic processes. In the model 2 we have presented the definition of stochastic process and its properties. Stationary processes discussed in model 3. Discrete time Markov chain is discussed in model 4. Continuous time Markov chain is discussed in model 5. Martingales are presented in model 6. Brownian motion and its properties are discussed in model 7. Now we are giving the presentation on model 8 renewal processes. In this we are planning to give lecture for 5 hours, starting with renewal function and the renewal equation in the lecture 1, generalized renewal processes and renewal limiting theorems in lecture 2, and in the lecture 3 we are planning to present a semi-Markov process or Markov renewal process and Markov regenerative process. And in the lecture 4 we are planning to present non-Markovian queues. In the lecture 5 we are planning to present non-Markovian queues with respect to the service distribution. In this lecture we are planning to give the definition of a renewal process and the related properties. Then we are going to present a renewal equation, and then we are going to present renewal times. Then finally we are going to explain what is the meaning of age, excess and the spread at time t. The renewal theory is the branch of probability theory that generalizes Poisson processes for arbitrary inter-arrival or holding times. Renewal, as the word suggests, means that an event occur again. In this, when we say that x1 is the time of first renewal, then it refers to the first time an event occurs, where event may be defined as required by the user. Let x1 be the time to the first renewal, and let xn, n running from 2, 3 and so on, be the time between n minus 1th renewal and nth renewal. Assume that xi's are independent, identically distributed random variables with the distribution function capital F. The mean for the random variable xn, that is denoted by the mu, that is nothing but 0 to infinity x times integration with respect to df of x, which will be positive because xi's are nothing but the time between the n plus 1th arrival to the nth arrival, that is a random variable xn. Hence the mean will be a positive. Define the time of nth renewal by Sn is a summation of first xi random variables. The xi's are nothing but the time interval between the I minus 1th renewal to the ith renewal, and Sn is nothing but the time of nth renewal, that is denoted by summation I is equal to 1 to n xi. So for every n you will get a one random variable Sn. So S1, S2, S3 and so on. So this is the time of nth renewal. That's a collection of random variables. the another random variable, let nt be the number of renewals by time t. So that n of t is the maximum of n such that Sn is less than or equal to t. That is nothing but how many renewals takes place on or before time t, that will be the random variable n of t. So one can relate nt with Sn with this formula, maximum of n such that Sn is less than or equal to t. So the n of t is nothing but counting how many arrivals, how many renewals takes place till time t. Therefore, this is a counting process, and this counting process will be a renewal process. If for some n Sn is equal to t, that means a renewal is said to occur at time t, or Sn gives the time of nth renewal and is called the nth renewal time. Sn is equal to t, that is nothing but the nth renewal time. Let us see the sample path of a renewal process. In this sample path of renewal process, the x-axis has the renewal time points. Renewal time S1 is the first renewal, the time in which the first renewal takes place. S2 is the time in which the second renewal takes place. S3 is the time in which the second renewal takes place. The x1 is the time between the first renewal and the second renewal. The x2 is the time between second renewal and the first renewal. And xi is nothing but the IID random variables with the distribution function capital F of x. Since it is in between the renewal time between the renewal time, therefore the mean will be a positive. So in this sample path we are giving the different values of x1, x2, x3, and what are all the different time points in which the renewal takes place, that is S1, S2, S3, S4, S5 and so on. And in the y-axis we are making a count n of t. So till some time the renewal is only 1, after some times the renewal is 2. So suppose you stopped it somewhere and asking how many arrivals takes place at this much time. Therefore 2 arrivals takes place at this much time. After crossing, suppose I stopped it here, then there are 4 arrival takes place at this much time. Therefore the n of t is equal to maximum of n such that Sn is less than or equal to n, Sn is less than or equal to t, makes the possible values of n of t. So n of t for possible values of t, that will be a stochastic process, it is a counting process, and this is a renewal process also. And xi's are the IID random variables, and Sn is the time of nth renewal. A common feature is this example thus is that rather than studying a random value of a sum of fixed number of random variables, one investigates the random number of terms required in order for the sum to attain a certain deterministic value. For non-negative summons, we are lead to the part of probability theory called the renewal theory, and the summation process Sn is called the renewal process. So this is the connection between the random walk and the renewal process. Now we are moving into the remarks of a renewal process. The first remark, a counting process for which the inter-arrival times are IID random variables with arbitrary distribution is said to be a renewal process. Whenever you have a counting process in which inter-arrival times are IID random variables with whatever be the distribution, with the arbitrary distribution, is said to be a renewal process. Second remark, a Poisson process can be defined as a counting process for which the inter-arrival times are IID with the exponential distribution. So the Poisson process is a special case of a renewal process in which the inter-arrival times are exponential distribution. IID as well as each has exponential distribution. Identical, independent and identically distributed random variable. A renewal process is more general counting process than Poisson process. A renewal process is more general counting process than Poisson process, because in the Poisson process the inter-arrival times are identical, independent and each one is exponential distribution, whereas in the renewal process it could be any arbitrary distribution. Any counting process need not be particularly Poisson process. A continuous time, third remark, a continuous time stochastic process in which the embedded jump chain, that is nothing but the discrete process registered what values the process takes, is a Markov chain, and where the holding times, that is nothing but the time between jumps, are random variables with any distribution whose distribution function may depend on the two states between which the move is made. We say it is a semi-Markov process or Markov renewal process. If this condition is satisfied by a continuous time stochastic process, it has the embedded Markov chain and the holding times depends, it can be any distribution, but it depends on the two states between the system moves, then the corresponding stochastic process is called a Markov renewal process or semi-Markov process. We are going to discuss the Markov renewal process or semi-Markov process in lecture 3 in detail, and the application of semi-Markov processes in queuing models will be discussed in lecture 4 and 5. The remark number 4, when the probability of x takes the value some constant c is equal to 1 for some constant c greater than 0, then the corresponding renewal process is called a deterministic renewal process. This x is nothing but the inter-arrival time. For renewal process, the inter-arrival times are IID random variables. Therefore, for one random variable, we are defining it's a constant random variable. If these IID random variables are constant random variable for some constant c greater than 0, then the corresponding renewal process is called a deterministic renewal process. Now we are going to discuss the distribution of a renewal process. Consider a renewal process Nt with the inter-arrival time distribution f. We can relate the event Nt greater than or equal to n with the Sn less than or equal to t. The event Nt greater than or equal to n is nothing but the number of renewals that takes place till time t is more than or equal to n. The event of Sn less than or equal to t means the number of renewals, the n number of renewals takes place on or before time t. So both the events are same. Therefore, the probability of nt greater than or equal to n is same as the probability of Sn is less than or equal to t. That we are going to denote as the f superscript n of t. That means it is a n-fold convolution of the distribution function f. So this is the distribution of the nth renewal Sn, the distribution of nth renewal Sn. So using the distribution function of nth renewal that is Sn, you can find out the distribution of n of t. Since n of t is a counting process, the possible values of n of t is 0, 1, 2 and so on. So we can find the probability mass function for the random variable n of t for fixed t. So the probability mass function for the random variable n of t for fixed t is probability of nt is equal to n is nothing but, what is the probability that more than or equal to n renewals takes place on or before time t minus what is the probability that n plus 1 renewals takes place more than or equal to n plus 1 renewals takes place on or before time t. That difference will be the probability of n renewals takes place on or before time t. So since we know that this relation n of t greater than or equal to n is same as the probability of n of t is greater than or equal to n is same as probability of Sn is less than or equal to t, that is nothing but the n-fold convolution of f. Therefore, probability of n of t greater than or equal to n will be f superscript n-fold convolution of f minus n plus 1-fold convolution of f at time t. So once you know the inter-arrival time distribution f, you can find out the n-fold convolution. Once you know the n-fold convolution of f, using this formula you can find out the probability mass function of n of t for fixed t. For example, when inter-arrival time is a normal distribution, for example, when inter-arrival time is a uniform distribution between 0 and 1, the n-fold convolution of f is given by f superscript n of t is nothing but t power n divided by n factorial, where t lies between the interval 0 to 1. So this can be proved by the mathematical induction. So we can start with the n plus 1 fold convolution of f, that is nothing but the distribution function of the random variable Sn plus 1, that can be written in the conditional distribution. The probability of Sn plus 1 is less than or equal to t given Sn is equal to x, that is same as what is the probability that the inter-arrival time of the n plus 1th renewal takes less than or equal to t minus x, because the given Sn is equal to x and what is the probability of n plus 1 is less than or equal to t, that is same as what is the probability of xn plus 1 is less than or equal to t minus x. You can substitute and after simplification we can get the n plus 1th convolution of f, that will be t power n plus 1 divided by n plus 1 factorial. Hence proved the n-fold convolution of f will be t power n by n factorial for n is equal to 1, 2 and so on, and t lies between 0 to 1. Now we will discuss the other example and find the distribution of n of t. The Poisson process is a renewal process or counting process whose inter-arrival time has a exponential distribution with the parameter lambda. Since the inter-arrival times are IID random variables, each has the distribution exponential with the parameter lambda. Using the earlier form of writing distribution of nt in terms of n-fold convolution, you can find the distribution of n of t. So here for arbitrary n, first we know the distribution of n of t because it is a Poisson process, therefore it is e power minus lambda t power n by n factorial. Since you know the probability of nt is equal to n, you can find out the inter-arrival time distribution. The inter-arrival time distribution, for that you can go for finding the complement CDF of the random variable xn. So the probability of xn greater than x for arbitrary n, that is nothing but, since the inter-arrival times are independent, you can find out the probability of xn is greater than x is same as the probability of nx equal to 0 given n of t minus 1 is equal to n minus 1. That means what is the probability that n minus 1 renewal takes place till the time point t n minus 1, and given this situation, what is the probability that no arrival takes place in the interval t n minus 1 to t n minus 1 plus x, or since it is inter-arrival times are IID and stationary also, the n of x will be 0, finding the probability of n of x equal to 0 given that n of t minus 1 is equal to n minus 1. Since you know the distribution of n of t, you can substitute and you can get it is e power minus lambda x for x greater than or equal to 0, and this is valid for arbitrary n. So since the complement CDF is e power minus lambda x, the distribution of x will be exponential distribution with the parameter lambda. So to conclude, inter-arrival time is exponential distribution. We are using the property of Poisson process and the definition of the probability mass function of Poisson process also. Next we are going to consider one more example for the renewal process. Suppose that in a system a unit fails according with the Poisson process with the rate lambda is equal to 3 per day. So this is the example for Poisson process, a special case of renewal process. Suppose that there are 6 spare units in an inventory and the next supply is not due in 4 days. Our interest is to find out what is the probability that the system will be out of order in the next 4 days. That is nothing but what is the probability that at the time point 4 the number of fail units in the system is greater than or equal to 7. That is the probability of system will be out of order in the next 4 days. So this probability is same as 1 minus the summation n is equal to 0 to 6, the probability that n of 4 equal to n. You substitute the probability mass function, the lambda value, and the t equal to 4, you will get the required probability, that will be 0.954. So, this is the example of a Poisson process. This is the pictorial representation of a Poisson process and all other process in one graph. The Poisson process is in the PP. Poisson process is a special case of a pure birth process, and a pure birth process is a special case of birth death process, and birth death process is a special case of a continuous time Markov chain, and the continuous time Markov chain is a special case of a Markov process, and the Markov process is a special case of a semi-Markov process, and the semi-Markov process is a special case of a Markov regenerative process. The other side, Poisson process is a special case of a renewal process, and the renewal process is a special case of semi-renewal process, and the semi-renewal process is a special case of counting process. So, this is the way one can relate the Poisson process with the all other stochastic processes. Now, we are moving into the concept called renewal function. Let m of t is equal to expectation of n of t for fixed t, that is called the renewal function. Since n of t is a counting process and the possible values are 0, 1, 2 and so on, you can find out the expectation of n of t with the summation n is equal to 1 to infinity of probability n of t greater than or equal to n, since it is a discrete random variable with the possible values are 0, 1, 2 and so on. Since for fixed t, n of t is a discrete random variable with the non-negative integer values 0, 1, 2 and so on, the expectation is the sum of its complementary cumulative distribution function. Alternatively, the expectation can be computed as a sum of n times p n of t, that is same as sum of n times capital F n of t minus capital F n plus 1 of t, which gives sum of f n of t. The expected number of renewals up to time t first moment is referred to as a renewal function, that is capital M of t, that is equal to expectation of n of t. We know that the probability of n of t greater than or equal to n, that is same as the probability of Sn is less than or equal to t, and that is nothing but the CDF of Sn, that is nothing but the n-fold convolution of f. Therefore, summation of probability of n of t greater than or equal to n is same as summation of n-fold convolution of f, where n is running from 1 to infinity. So, using this one can find the renewal function, and the derivative will be the renewal density function of the renewal process. So, the capital M of t is a renewal function, and the small m of t, that is nothing but the derivative of renewal function, is called a renewal density function. The function small m of t specifies the mean number of renewals to be expected in a narrow interval near t. One can find the renewal density function using limit h tends to 0, the probability of one or more renewals occurs in the interval t to t plus h divided by h. That is nothing but limit h tends to 0, 1 by h, the probability of 0 or more renewals, that is nothing but the summation of n is equal to 1 to infinity of probability of n renewals in the interval t to t plus h. The limit and the summation can be interchanged, and the probability of n renewals in the interval t to t plus h, where n is running from 1 to infinity, that can be simplified in the form of n-fold convolution of f between the interval t to t plus h. By using the m of t is nothing but the summation of fn of t, therefore the limit h tends to 0, 1 by h of fn of t plus h minus fn of t is nothing but the derivative. Therefore, it is a capital M dash t. So, the derivative of renewal function is nothing but the renewal density function. For example, the renewal process whose inter-arrival time follows IID with the uniform distribution between the interval 0 to 1, the renewal function is e power t minus 1, because inter-arrival time is uniformly distributed between the interval 0 to 1. Therefore, you know what is the fn of t, n-fold convolution of f. Substitute that is t power n divided by n factorial. After simplification, you will get e power t minus 1. That is the renewal function for a renewal process whose inter-arrival times are IID random variable with uniform distribution between the interval 0 and 1. Now we are going to relate the probability density function of inter-arrival time with the renewal density function and renewal function in Laplace form. We know that the renewal function is nothing but the summation n is equal to 1 to infinity fn of t, n-fold convolution of f, where f is the CDF of inter-arrival time. In equivalent form, using the Laplace transform, the m star of s, that is nothing but the Laplace transform of m of t, renewal function. That is nothing but summation n is equal to 1 to infinity the n-fold convolution of f in Laplace transform as a function of s. That is same as the small f of n-fold convolution in Laplace form divided by s. We know that the derivative of n-fold convolution of CDF is nothing but the n-fold convolution of the probability density function. So, this can be written as 1 divided by s, summation n is equal to 1 to infinity the Laplace transform of probability density function power n. You can simplify. After that, you can find the renewal density function in Laplace, that is nothing but f of s divided by 1 minus f of s, where f of s is nothing but the probability density function in Laplace transform. From the same equation, you can get the f of s in terms of m of s also, where m of s is the renewal density function in Laplace. Now we are moving into the next concept, that is called renewal equation. It can be shown that the renewal function m of t uniquely determine the inter-arrival time distribution f. For example, m of t is equal to lambda t corresponds to the exponential distribution break. Now we are moving into the next concept called renewal equation. A renewal equation is expressed by a recursive form through an integral equation. We know that the renewal function m of t is expectation of n of t. This can be evaluated by conditioning on x1, that x1 is nothing but the time of first renewal. Hence, the renewal function m of t is equal to integration 0 to infinity expectation of n of t given x1 is equal to x, integration with respect to the CDF of inter-arrival time distribution. This integral can be evaluated by dividing into two cases. One is the case where the first renewal occurs after time t, and the other is the case where the first renewal occurs before time t. In the former case, since there are no renewals observed by time t, the conditional expectation will be 0. In the later case, the first renewals occurs before time t, and the expected number of renewals between x and t will be the renewal function m of t minus x from the definition of renewal function. Hence, the conditional expectation is one renewal already takes place before time t, therefore 1 plus the expected number of renewals between the interval x to t will be m of t minus x. Therefore, the conditional expectation is 1 plus m of t minus x. Therefore, the m of t, that conditional expectation integration, will be splitted into 2. Hence, the one integration will be 0 because the conditional expectation is 0. The other integration will be 0 to t 1 plus m of t minus x df of x. That is same as capital F of t plus 0 to t m of t minus x df of x. So, this integral equation is called the renewal equation if m is considered as unknown, because the left hand side is the m of t, that is a renewal function. If m of t is a unknown, then m of t is written in the form of m of t is equal to f of t plus integration 0 to t. The integrand is m of t minus x. Therefore, this is called the integral equation, and this integral equation is called the renewal equation. Later, we are going to give the renewal limiting theorems as a t tends to infinity for the integral also. M of t minus x df of x can be evaluated as a t tends to infinity if certain conditions are satisfied. But here we are presenting the renewal equation where the renewal function is considered as unknown. The above equation can be written as m is equal to capital F plus m star small f, where small f is nothing but the probability density function of inter-arrival time. Now, taking a Laplace transform on both sides, you will get m star is equal to f star plus m star small f star. You can relate f star is equal to f star by s, where star is nothing denoted for Laplace form. And simplifying, we get f of s equal to s times m star divided by 1 plus s times m star, where capital M star is nothing but the renewal function in Laplace. The renewal equation can be generalized for some unknown z of t, unknown function associated with the renewal process, with the distribution function capital F as z of t is equal to q of t plus integration 0 to t z of t minus x df of x. So, the renewal function can be extended, can be generalized for any unknown function associated with the renewal process, that is z of t as q of t plus integral 0 to t z of t minus x df of x, where q of t is a known function. It can be shown that the renewal function uniquely determines the interarrival time distribution. Once you know the renewal function, you can uniquely determine the distribution function. For example, if I know the renewal function is lambda t, then you can say that the interarrival time distribution is exponential with the parameter lambda. Hence, the renewal equations are useful for deriving the quantity of interest associated with the renewal process at a function of time. So, first we discuss the renewal equation in terms of renewal function, and this can be generalized to any unknown function of time which is associated with the renewal process also. Now we are moving into the next concept, renewal times. Let x1, x2 be the time between its successive occurrence, then s0 is equal to 0 and n plus 1 is equal to sn plus xn plus 1 defines the time of occurrence, assuming that the time origin is taken to be an instant of such occurrence. Then the sequence Sn is called the renewal process, provided the inter-occurrence times are IID non-negative random variables. Then each Sn is called the renewal times. Note that the renewal process is said to be recurrent if xn is finite almost surely for every n. Otherwise, the renewal process is called a transient. Now we are moving into the last concept in this lecture, that is age, excess and spread. Suppose nt is a renewal process and Sn forms the renewal time. You can define age at time t of the renewal process as a of t is equal to t minus s suffix nt. The excess at time t of the renewal process is defined as y of t is equal to s of n plus s of n plus t plus 1 minus t. That is the excess at time t. Whereas the spread is the addition of age and excess, that is a spread of spread at time t of the renewal process. Here we are going to calculate what is the average excess or expectation of excess. Let yt be the excess at time t and let gt be the expectation of excess at time t. Using the renewal equation which we have discussed now, we are going to find the expectation of excess at time t. First we are making condition on x1 and the conditional expectation will be expectation of y of t given x1 is equal to x, which is greater than t, will be x minus t, while x1 is equal to x which is less than t, then the conditional expectation will be a unknown still g of t minus x. Therefore, the g of t will be two integration. One integration is from t to infinity and the integrand is x minus t, and the second integration 0 to t and the unknown is g of t minus x. Since g of t is an unknown function of time t, this is an integral equation. One can solve the integral equation. This is nothing but the renewal equation. One can solve the renewal equation and obtain g of t. Here is the list of reference for lecture 1.